So this is 129S. And I should mention there's a lot of special events coming up. Sans Holiday Hack Challenge just opened. You can do this if you want. It's very popular. Tons of people do it. It's sort of like a video game you play, calling out characters, and you get to see hacking challenges, and you get to see little movies that show you how to do it and such. They work very hard on this. SANS is the #1 cybersecurity education group. Their classes are great. They're just too expensive. And so this is a fun way to do it. So check this out if you're interested in finding something fun to do over Christmas. It's already open much earlier than usual. And they say it sounds like more fun than usual and such. A lot of things are happening. This weekend we have CPTC, but this is only for people on the team. There's no way for spectators or random students to join, which is a shame. But so most people can't come to this, but you can come to this. On November 23rd is a CCDC Invitational. Anybody can come. This is where you practice defending your machines against attackers that are attacking them. And if you get to see how it works. The advent of code is the thing I like. That's starting December 1. This is just a series of coding challenges, so it's only for people who enjoy programming, but I do, and I practice it every year. And we're a workshop. This date is not completely confirmed yet, but I think it'll be December 7, a free workshop all day on hacking and penetration testing from this guy I know named Dave Porcello, who's worked out a course, and he's going to teach it to us for free. This date may change, though, I'm warning you. And the WISIS party, Women in Cybersecurity, coming on December 9. And I think that's it for this semester. Lots of events. At this time of year, there's always tons of special events. So, Ignite, tomorrow has an event all day with Palo Alto Network Security. Ignite on Tour Bay Area. Oh, okay. Well, that's interesting. All right. Yep, so many events this time of year. Anyway, the chapter today is application logic. And this is the stuff that's hard to scan with an automated scanner. This is where you just have errors in the way you plan your app. They don't have a common signature, because developers make some kind of assumption, which leads to problem. There's just about 10 case studies is all this is. So here, you have a remember me function, which sets a permanent cookie. That's usually how you work. A cookie should be random. But it turns out that instead of using a random cookie, they encrypted a string that contains your name, user ID, and other data like the time or something, including IP address. And this is, you may remember in previous chapters we talked about it, this is an unwise thing to do. And here's one of the many reasons why it's unwise. Because you have other things you might want to encrypt. The screen name is also stored in an encrypted form. And that's the flaw. What the developer did was to use the same encryption algorithm for both cookies, the one that remembers your screen name and the one that is your session cookie to show you've logged in. And the problem is the user can control the screen name. And the screen name cookie is encrypted, but it decrypts in the app and shows you your readable screen name on the form, on the page. Therefore, you can copy the remember me cookie into the screen name cookie, and it will decrypt it. And now you can see it says welcome Marcus and then some numbers like your IP address. So you can change your screen name to this, and it will encrypt it using the same routine, so you can forge a cookie that makes you the administrator. So this is a problem. I remember this happened to Facebook. When you reset your password on Facebook, it would send you a link, and the link had this long random thing in it. And one of the pen testers found that there was somewhere else on the page where the same routine was used to make that random thing. So you could go to somebody's page and look at something like the URLs for the images, and you would find the random number that was going to send them to reset their password, so you could reset somebody else's password and get in their account. It's the same kind of problem. All right, so that's the game. And I say the encryption was unbreakable. They weren't able to crack it. They didn't have the key, but you don't need to. You can find some part of the app that lets you encrypt and decrypt things using their algorithm. All right. So here's the steps to find these things. Look for things that are encrypted instead of being hashed with data from the user, and try substituting other encrypted values you find. See if you can copy them around. You can also exchange blocks of data. So there's plenty of ways to use encrypted data and manipulate it, even though you can't decrypt it. And then there's a password change function. So you have password change, typically asks for username, the old password, and 2 copies of the new password. Then you can change your password. However, in this case, the administrators had a form to change any password implemented by the same server-side script. And the way they wrote it is the administrator's form doesn't ask for the existing password. So if they get a request without an existing password, they interpret that as coming from the administrator. If they get one with an existing password, they interpret that as coming from a user. So all you have to do is take the request from the form and remove the existing password, and it will misunderstand you as being the administrator and let you in. This is quite common. Again, people just, the fundamental flaw with all these attacks is the developer makes certain pages, and they assume that you are just using those pages. So you can't get to the administrator page, so they think you can't create the data that appears to be sent the way the administrator page would send it, but that's not true, of course, if you have a tool like Burp. And you can see they test these things so they work under normal conditions, and they don't think of these tricky attacks. So here's the step. Try deleting parameters. Want to have another, delete parameters and see what happens. Here's one for checkout. You add items to a shopping basket, return to the shopping basket, finalize the order, enter payment information, and enter delivery information. And they assume that you're doing these steps 1, 2, 3, 4, but they did not enforce that by having a hidden form field that was random. So you can use forced browsing. You proceed directly from step 2 to step 4. You add it to the packet, finalize the order, and then you don't submit payment, but you go to delivery information. But the developer assumed that the only way you can get to page 4 is by passing through page 3. They didn't verify that you actually paid for it, so you can get a product without paying for it. This kind of thing happens all the time. Some Microsoft at one time was giving away free USB drives, and you could use Burp to get like 100 of them. You could remove the counter that says how many have you already got, and just keep getting more, that sort of thing. So you just try skipping stages, do a stage more than once, doing them out of order, look for the URLs and such, and see if you can figure out ways to fool it. Here's another one. People obtain quotes for insurance, and then they submit an application. It has a whole bunch of stages. They submit basic information. The app computes some values. Then across many stages, you give it tons of information. It finally is sent to a human who will decide whether it approves your request for insurance or not, whether you appear to be qualified and have enough money to pay for it and all that jazz. And each stage, it uses the same app that the user uses to submit it. And so each request, the assumption they made is that each request will only include the parameters in the previous page's form. The same flaw again, they assume the pages are used in order, and the only data on the page is the page the developer put on the form. So if you have a user that can submit extra parameters, then the user can supply valid data at an earlier stage, but then override it later. So they can change things. And so this way they're able to inject code into something like a name and reveal personal information. So that's the first flaw. But the more serious flaw is they were able to get approval at a certain premium and then change the premium later. So they get the insurance at a lower price. And they could also force approval. The underwriter sets a flag like approved or unapproved with their form, and they could change, the attacker could set that flag bypassing the actual underwriter. This sort of thing, putting in parameters out of sequence or extra parameters, you can fool the server. And this one version of this is called parameter pollution. We talked about it last time, where you set the same parameter twice, and that can often confuse web pages. So you take parameters from one stage, you add them to requests from another stage, and so on. Just try adding them out of order and see if the web page misunderstands them. Now here's one where you could log in, you could register for online banking. It collects a bunch of data, forwards it to a back-end system which mails a letter to you containing instructions. And so they've regarded this as safe. It has 3 layers of protection. Some personal data is required to start it. A secret one-time password is sent as a physical letter, so you can't steal that on the web. And you have to call in and authenticate. So they felt like this was quite secure. Now the problem is the customer information was stored in a database as this object with first name and all this other information about the user. And so the attack is when you register a new account, it's the same data object also used for online banking. So, and the account details on the e-banking page are generated from the customer number. So what you can do is log in with valid credentials, then go to the registration section and submit a different customer's name and address. And now the app will overwrite the object with the new object pointing to the targeted customer, so you can move from your account to somebody else's account by confusing it, by changing the name. All right, that's the same. So the fundamental flaw is you can write the same database object two ways. The main banking function, you have to log in. They have to know who you are. But when you're registering a new account, you write without having previously logged in, and yet you're still writing to the same object. So that's the fundamental flaw. And here's another one. You can transfer funds between accounts, but you're only allowed to transfer amounts up to $10,000. Larger transfers require senior manager's approval. So here's the actual code. If the amount is less than $10,000, then it's okay. It doesn't require approval. Otherwise, it does require approval. But this is the simplest one in the world. Just transfer a negative amount. And it will be going in the other direction, but it will be interpreted as not requiring approval because it's less than 10,000. This happens all the time. There's also integer overflows where you put in some unthinkably huge number, like hundreds of billions, that's so large it rolls around and becomes negative. That was used to steal $1 million from a cryptocurrency a few years ago. You could just put in a huge number and it would interpret it as a negative number and move the money backwards. So that's true of all numeric limits. All computers have number limits. Many of them have this problem of rolling over. If you write in safe languages like Rust, that doesn't happen. But dangerous languages like C, if you just keep adding and making a number bigger, it will roll around and become negative. And so again, just putting negative values for all numerical values and very large values that you may find unexpected behavior like this. Here's a simple one, cheating on bulk discounts. You order some products, and if you buy a bunch of products together, you get a discount. So what you do is you add them all to the shopping basket, and then you remove someone from the basket, but you already got the discount. So it's a simple flaw, but again, they just didn't think of that. Here's another one that's kind of amazing. So there's a web interface for an intrusion detection system, user-controlled input, and it's to be put in a command, like the ping form that you exploited earlier in this class. But the developers tried to prevent code injection by looking for special characters and adding a backslash in front of them, which means they will not be interpreted as a control character. So now if you put a semicolon in, it'll put a backslash in front of it, which means the semicolon is just a character. It does not mean that after this is coming another command. The problem is the developers forgot to backslash the backslash itself. So if the attacker ends foo backslash semicolon ls, it will add another backslash to the backslash. Or it will not add another backslash to backslash, it will add another backslash to the semicolon, and these backslash means it doesn't have the effect of escaping the next character. So now you get the semicolon through, and now you can do code injection. And this is why, like I mentioned before, a deny listing is a very unsafe procedure. If you try to enumerate all the bad things and make sure to remove them, you're very likely to miss some. What's much safer is to enumerate the good stuff and only let stuff through that you recognize as good, like nothing but numbers, letters, and spaces, something like that. And then here's another one, of course. You have a SQL injection filter to try to stop people from putting in apostrophe or 1 = 1 and other SQL injections. So what you do is you change all quotes to double quotes, which is the correct way to escape a quote in SQL. So it's not interpreted as the start of a string. That'll be interpreted as just a literal quote. But then you have a length limit that limits the input to 128 characters. So it's obvious what you can do. If you put in normal input, like this one, apostrophe dash dash, it'll be change it into apostrophe apostrophe dash dash, which will not bypass the login. But what you do is you put in 127 A's followed by a quotation mark. And now when it tries to add the second quotation mark, it hits the length limit and trims it off. And so, of course, your two security measures have worked in a way that one undoes the other. All right. And so you can, if you want to find these, you can submit strings like this, just put in a whole lot of dashes and a letter and a whole lot of dashes. And if it hits some kind of limit, then one of these will have an odd number of apostrophes, and that'll create a syntax error. The other will have an even number, and it won't be a syntax error. And so that would detect this kind of problem. And you might think no one would be stupid enough to put in those two tests in that order, but it can easily happen because you might be using different devices. You have a web application firewall, and then you have an application, and it might be running a software web application firewall. It's entirely possible that these two operations are done by different devices at different times on the way to the app. So it's not as obvious to the developer as you might imagine it is, that these two security measures have in fact canceled each other out. And here's another one. You have a bunch of information only accessible to paying subscribers, but they give you a search engine. And this is why I was just giving a talk recently. They were talking about how it's okay to use public large language models for medical data as long as you anonymize the data. And I said, no, don't do that. People have tried that. It turns out if you have supposedly anonymized data, it's pretty easy to figure out who people are anyway. So here we have document titles like this, press release, annual results, and so on. And the idea is you cannot get information from the search engine, but you can. It's just like blind SQL injection. What you do is you guess at the contents, and see here, I do consulting, and I find 276 matches. The only thing I get is the number of matches, but now it's like 20 questions. I try merger, but there's none. I try share issue, dividend, but takeover, there's a match. So there is an article about a takeover. So now is it taking over this company, that company, that company, that company? Oh, it's taking over this company because there's a match. So that's the same thing. Just the fact that I can tell how many matches there are, I can deduce what's in these articles that are supposed to be confidential. And this applies to like military systems too, where you have a low privilege user that can deduce information about the secret stuff they can't access directly from some information like a search engine. It's called an inference attack, I think. All right, and so people have used this. They've used it to brute force passwords from a configuration file by searching and guessing until they see a match. All right. And also you can use debug messages. There's an app that put out error messages, including all the URL parameters, which is really dangerous because those parameters often include a session cookie that will let you log in as somebody. And they thought, however, that you could only see your own parameters from your session. That was the idea, so it would just help you debug your own session, and there wouldn't be a risk. But they had a race condition. The data you saw on the screen did not come from your browser, it came from the server, and the server was just storing it in a temporary file, which was shared. So that means if the app gets active, and a lot of users are using it at once, another user's error message might come through to you, because you write an error message, and before you read it, somebody else writes one, and you're using a shared object. This is how race conditions happen. And so that's the problem. I've seen this many times. I remember there was a time like 10 years ago when a small number of users logged into either Yahoo or Gmail and they saw other people's mail. This kind of thing happens every now and then. And it's real hard to catch because when you test apps, under test conditions, you have just a few users. When you deploy them, you have millions of users. Now you'll suddenly have users using it at the exact same time, which wouldn't happen under a normal test condition. That's race conditions. And so you can also just do this. You can just pull the container repeatedly to see what error messages appear, and you'll just see various error messages appear with other people's usernames and session tokens, so you can just sort of get them out. All right. And here's another one, multi-stage login process with several factors of authentication, which was considered highly secure. But sometimes it had this problem. I see a customer would log in and they'd see somebody else's account. They couldn't figure out why. But they eventually found out it happens, of course, when two people are logging in at the same time. And so what happens is it stores an identifier about you in a static non-session variable, which is read back an instant later, and this is what they call race conditions, time of check, time of use. You write something, then you read it at a later time without understanding that another process might have changed it in the meantime. And so that's what caused it. It was using static storage to store something that should have been stored in something per session. Each session ought to have their own variable, which is not shared with another session. But they didn't. So to catch these things, you just have to look at how your, all these logic flaws, you have to sort of have a block diagram showing, here's what we collect, here's the next step, here's the next step, and then you have to think about what assumptions have you made and what would happen if things happen out of order or with unexpected information being added at different steps. So you have to have good comments, understand what each component does, write down the assumptions you've made. This is the hard thing about coding. You can write sloppy code, like a pen test tool to break into a system pretty easily. That's what I do when I teach Violet Python. But to write real professional code, you really have to think about everything that can go wrong and make sure you've handled it correctly. And that is very difficult. So reflect on every assumption, think about what circumstances would violate the assumptions. Think about what the user can control, and think about how the app will handle unexpected behavior and side effects of your various operations, how they might undo each other's. And there's no general recipe or automated scanner that can stop these flaws. It's just human intelligence thinking about the logic of your app is the only way to prevent these things. All right, so that's it for the chapter. There are no cahoots for this.